This is problem 67 in chapter 18. This is the one with the charge and the two charges, excuse me, and the two springs, and they're separated by distance 0.05. That was some scratch work to make sure I can draw a decent picture here for you guys. And I'm going to draw the starting, because these distances are all really important. And starting out, the two charges are separated by 0.05 meters, and that is given in the problem. Move this off to the side a little bit here. All right, so 0.05 meters. And so there we go. Sorry, moving around a lot. I'll stop that. So 0.05 meters is the separation between them initially when they're uncharged. And now they give them a charge, and it says in the problem, you can read it, that the separation doubles. So I'm drawing our picture here. This distance between them, doubling it, is now 0.10 meters. And that's because they have the same charge, and they're repelling each other to 0.10 meters. And they're hooked up to these springs. So here there was no charge. And here we have a charge. And I believe, if I remember correctly here in the question, it asked us to find the spring constant of the springs, and it also gave us the charges. They each have 1.6 microcoulombs. So 1.6 times 10 to the negative 6 coulombs. That's the charge on each one of these in this second picture. And if we're looking for the spring constant, I know at some point I'm going to use F equals Kx, or if you want to throw the negative on there, that's fine. But I'm looking for K, so I'm going to have to know X, and I'm going to have to know F. I'm going to pick an object here, because if I want the force of the spring, I have to account for the fact that the spring is pulling on the charge, okay, or pushing on the charge, and so is the electrostatic force. Because remember, these are both positive, so positive, positive. And I'll draw the free body diagram for this one. You could just as well do the free body diagram for this one to try to get to this force of the spring. Well, remember, they were pushed this way by the electrostatic force. So the spring is actually going to push on this charge to the left. So I'm going to have force of the spring, I'll just call it F sub S, to the left. And then we'll have the force due to the charge to the right. I'll call it force sub E, whatever you want to call it. Okay, so that's what's going on there. And if we're not moving at this point, of course, these two are equal, or they add up to 0. So I'll sum my forces in the x direction, set equal to 0. So we'll have force of, we'll call right positive. So left's negative. So I'll have negative force of the spring plus force E equals 0, or Fe equals Fs. So this is good news. If I can get that electrostatic force and X, okay, the displacement of the spring from equilibrium, which we'll have to think about, then I can get K. So I'm going to have to get these two things. So this, with my similar notation down here, this is Fs, and this is a very specific X that we'll talk about in a little bit. But before we do all that, let's get this Fe. Let's figure out what this is, this electrostatic force. Well, for point charges, we can apply K, Q1, Q2 over R squared. Call this Q1, Q2. But they carry the same charge. So these will both be Q. So I'm going to change this into K Q squared over R squared, only because these two charges are the same. Okay, let's plug in and see if we can get this number. This is my Fe. So K is 9 times 10 to the 9th. I better double check that. It's a constant. You can look it up on your table of information. They have 8.99 times 10 to the 9th, close enough. And then it should be a Newton times a square meter over a Coulomb squared, so the units work out. You can see charge squared, so Coulomb squared down here. And then, yeah, that looks right. So that's my K. Really should have left more room here. I'm going to go ahead and just write it down here. So forget that. I'm going to rewrite 9 times 10 to the 9th. Units times square meter over Coulomb squared times my 1.6 times 10 to the minus 6 coulombs. And I'm doing that and that again. Same thing as having it squared, just algebra. Okay, if they were different charges, would not have done it this way. I would have had a Q1 and a Q2 over the distance between them, which I have on my picture right now is 0.10 meters. And then, of course, we have to square that. And then we'll get what that number is. 9 times 10 to the 9th times, I'm just going to do let's do it all in one step. 1.6 times 10 to the negative 6, that's squared. And then divided by 0.1 squared. And I'm getting 3.65 times 10 to the 13th. Let's see, 10 to the 9th, 10 to the 12th. That doesn't sound right. Let me double check here. 9 times 10 to the 9th. Oh yeah, that's not right. I messed up. I'm like, there's no way it can be that big. I'm going to calculate that again. Times. I was just, by the way, to check, to make sure it was reasonable, I was just looking at my exponents, and it did not make any sense at all. Times 10 to the -6th, and I had written, I don't know if you can see it or not, but I had 10 to the 0.6 right there, so that's what was messing it up. Squared. That whole thing squared. That looks right. And now divided by our 0.1 squared. That looks better. 2.3. And I knew that was way off, because if I have an exponent there, now remember, this is going to eventually be equated to the force of a spring. And having something like I did before times 10 to the 13th would be one heck of a spring. 2.3 newtons sounds more reasonable for what I know about springs. So we got our force of the electrostatic force there. And now we got to get this K. So I'm going to go in here. I'm going to put the 2.3 newtons in. Equals Kx. And I've already counted for the signs here and all that. Okay. So 2.3 newtons Kx, but now we've got to get what this X is. Oh, another thing to be careful of. This K is not the same as this K. This is that constant you look up, that's the 9 times 10 to the 9th. This is the spring constant. To avoid confusion, I'm now just going to put like a K1 on here in case somebody is zipping through just looking at the work, okay? And this K, I'll put a C for the constant, okay? Something like that, okay? And now we got to get this X. This X is not 0.1, okay? This will be the distance from our point we started at with our spring. So going back here, we're looking at how much is the spring squished or stretched from that starting point. So I'm going to add some lines here to make this clear. So I'm going to add, and oh yeah, let me take a look at my notes. See if I want to do it the same way. I'm going to split there and then in the middle. Yeah, okay. All right. And we need this distance, the part that the spring has been squished to the right or compressed to the right. And I'm going to add a line right here so that we can see that this right here, okay, from here to here is half of this. So if you look carefully, we got 0.05, and I've cut this in half. So that is point from here to here on my picture down to this dotted line is 0.025. Hopefully that makes sense. We got to have that one. I'm talking about that distance right down here on these pictures that are lined up. And this whole distance here is 0.1. Well, to the right of my solid line, from here to here will be 0.05. So if this is 0.05 and this is 0.025, this has to be 0.025. The distance on this half has to be the same as over here. That is how far this spring has been compressed. So now we can plug in a 0.025 and a 2.3, and hopefully we'll get our K1, which is what I'm claiming is the spring constant. So 2.3 divided by 0.025 is 92 newtons per, I forgot a unit. Are those in meters? Yeah, those are meters. Newtons per meter. So there's my spring constant. Let's check and make sure that we got this right for 67. Yep, 92 newtons per meter. The key, oh, actually, they did the intermediate step. I was going to say you might have like derived an equation for this and then plugged in, but if you do that, be very careful with the k's. These aren't going to cancel out, otherwise you would never solve, and you're not going to have like a k squared or anything like that. Okay, they're different k's. That's it for problem 67.